When we met the vector space axioms in our last video, we saw that they were abstractions of familiar properties of scalar multiplication and addition for actual column vectors or actual matrices. But there are some familiar properties of addition and scalar multiplication for vectors and matrices which weren't included on the list of vector space axioms. For example, we know that it's always true that if you scalar multiply a column vector by 0, you always get the 0 vector. And we know that it's true that if you scalar multiply a column vector by -1, you get the additive inverse of that column vector. So what that means is if you add 1, 2, 3 to -1 times 1, 2, 3, then you get back the 0 vector. So those are, in some sense, familiar properties of scalar multiplication and addition that hold for vectors or for matrices, but they're not on the list of vector space axioms. So are these things which just happen to be true in vector spaces which consist of column vectors or matrices, or must they be true in every single vector space? Well, the only way we can try to resolve that question is by trying to give a proof which uses the vector space axioms. If we can give a proof which uses the vector space axioms and only the vector space axioms, then we know that a particular statement which we can prove that way holds in any vector space whatsoever. So not just any particular vector space we were thinking of, but any vector space whatsoever. So let's look at one of those properties which we just met, the property that if you have a vector v and you scalar multiply it by 0, then the answer is always the 0 vector. We're going to give a proof that that is actually true not just in our familiar example of column vectors, but is actually true in every vector space. As I say, if we want to do this, we have to do a proof which uses, and only uses, the vector space axioms. So I've copied the vector space axioms for a real vector space at the bottom of this slide. Now, it doesn't matter here that we have only the axioms for a real vector space. The axioms for a complex vector space are the same, except you just replace the real numbers with the complex numbers. So this proof will work in any vector space, a real vector space or a complex vector space. Now let's see how this proof is going to work. So we'd like to show that the scalar 0 times the vector v is equal to the 0 vector. So what happens when I scalar multiply the scalar 0 into the vector v? So when I underline the v like this, I mean that v is this vector right here. It's a vector in v. So the underline is supposed to distinguish typographically a vector from a scalar. So the 0 there is the scalar 0, and the v underlined is this particular vector, this particular element of our vector space that we're talking about. So what can we say about this? So 0 is the same as 0 plus 0. So I could rewrite it like this. And now we can use a vector space axiom, namely axiom number 7, to rewrite this as 0 times v plus 0 times v. Okay, now let's think what axiom 2 tells us. Axiom 2 tells us that every vector has an additive inverse. So any vector in v, any element in v whatsoever, has an additive inverse. So axiom 2 says there exists an element, element x of v, with the property that x plus whatever this thing is, so we don't know what it is yet, but whatever this thing is, it has an additive inverse. So when you add it to its additive inverse, you get the 0 vector. So be careful with what's going on here. The symbols look a bit confusing. So on the right of that equality is the zero vector, the special zero vector in V. So this thing here. On the left we have a vector sum with this thing x and the scalar multiple 0 times our original vector V. Okay, let's add this additive inverse to both sides of the equation which we got at the top there. So when we do that, what we get is x plus 0v on the left, and on the right we will get x plus the scalar multiple 0v plus the scalar multiple 0v. Now, taking this one step further, we know what's happening on the left of that equation. We chose our vector x to have the property that when you add it to the scalar multiple 0 times v, you got the 0 vector. So on the left of this equation, we must have the 0 vector. 0 subscript v, the special 0 vector. And on the right, well, we can use the associativity property for vector addition to rewrite this. So why is this true? This is true because of the axiom number 3, which tells me that addition is always associative in vector spaces. Now, again, the meaning of x was that it was the additive inverse for our scalar multiple 0 times the vector v. So what you have in the brackets there is simply the 0 vector. So we've got the 0 vector for our vector space plus the scalar multiple 0 times our vector v. Okay, but now look at Axiom 1. Axiom 1 tells you that when you add the 0 vector on the left, you don't change the thing you added it to. So what we have now, finally, is just 0 times v. So we prove what we want to prove. The scalar multiple 0 times our vector v is equal to the 0 vector in our vector space. We now know, because we gave a proof only using the axioms, that this is not just a property which happens to be true for some vector spaces, so it's not just a property that happens to be true for column vectors, but it's true in any vector space whatsoever. Let's do another example of such a property. So the other property I showed you on the first slide, which is true for matrices and column vectors, but was not one of our axioms, was that if you add v to minus 1 times v, so you add a vector v to minus 1 times that vector, then you get the 0 vector. So that's a true familiar property of column vectors and column vector addition and scalar multiplication, but it's not one of the things on our list of axioms. So we don't yet know that it's true in every vector space. And we're now going to give a proof valid for every vector v in every vector space capital V by, just like before, giving a proof that only uses the vector space axioms and not the particular form of elements that a vector space might have. So here goes our proof. So we'll consider vector v plus minus 1 times vector v. What's that equal to? Well, look at Axiom 5. So Axiom 5 tells me that v is the same as 1 times v. So let's do this. 1 times v plus minus 1 times v. So that is by Axiom 5. This one here. Okay, let's keep going. We can gather scalars together. So look at Axiom 7. It tells me I can collect scalars when they're multiplied into the same vector. So this is 1 plus minus 1 times v. And the reason for that is that it's an instance of Axiom 7. Okay, keeping going, you have 1 plus minus 1 times v. Well, 1 plus minus 1 is 0. So that's the scalar multiple 0 times the vector v. But we've just worked out that for any vector space and any element vector v of that vector space, if you do the scalar multiple 0 times vector v, then you get the 0 vector. So this is 0, the 0 vector by the previous lemma. And we're done. We've proved our lemma. So that's an example of how you can prove that certain familiar properties of vector addition and scalar multiplication for column vectors and matrices, which might not be on the list of vector space axioms, would nevertheless hold for every single vector space, no matter what its elements look like.